Okay, I'm going to take and look at experiment number 3, Op-Amp applications number 2. And you might see I've got the circuit maker screen open already. I've already loaded the available circuit. Again, most of the circuits for succeeding experiments will be available on Blackboard in the folder for the experiment. Many of the experiments need to have the simulation up here set prior to the experiment working, and it is sometimes difficult to know what to set those parameters in the simulation analysis window. So I'm going to provide you with most of the circuits, and again, this is a circuit. This is called inverting amplifier number 1, and if you take a look at it, it's again a 741 op-amp. It's got 100K feedback and a 2.4K R in. Notice that the input goes now into the minus input of the op-amp, and so there will be a phase inversion of 180 degrees. So let's run it and take a look and see what happens. So my screen comes up, and click on this. Why we don't have anything, let's just go, here we go. If you discover a screen like that, again, one of the key things is to click on the counterclockwise arrow here and bring it back into, bring it to life, I guess. So we see the B signal, the green one, is the output, and the yellow one is the input. And it turns out that if I take this off automatic, the first one you want to take a look at, notice that the yellow one is going positive while the green one's going negative. I could blow this up to the entire screen here. And again, now it's more obvious. The yellow one's going upwards, the green one's going downwards. So there's a 180 degree phase shift. Let's take and lower this again if I can. I don't know if I'll be able to. Here we go. And let's bring this back to automatic. So using C and D, the cursors, what I discover here, C to D, is about 4.182 volts. I haven't, put them on there exactly, but again, you can at any time blow up the screen. That one's pretty close. I don't know about the bottom. Let's take a look here. Now we're off a little bit here, so we'll go and make that a little better. And then we'll bring the screen back. So here we have about 41.63 for the gain. Why do I say that? Because we know the input is 100 millivolts peak to peak, and the output is 4,163 millivolts. So I divide 4,163 by 100, I'll get 41.63. By the way, we have 100K ohm, let's stop it here, 100K ohm feedback and 2.4K input. So the gain for an inverting amplifier is simply RF over RIn. If RIn was 2.5K, the gain would be exactly 40. Since RIn's 2.4K, the gain is a little bit more than 40. So you can do the calculation to figure that out, exactly what the story is. The input offset voltage is always a problem with these things. If I was to use the op-amp as a very sensitive amplifier for a sensor, and the sensor only put out say a small DC voltage, what I might have to do is worry about what the op-amp's going to do. Will the output from the op-amp be accurate? So let's take a look. Let's blow this thing all the way up here and go over to the beginning. And if I click on this screen, you might notice that the signal is at 0 right here, but look at the output from the op-amp. It turns out that it's off from the 0 ground level. Also, if I went back, let's go like this, I would notice, I didn't take a look at it before, but notice my values of Y sub C and Y sub D. Those are the C and D cursors. And notice I have 2.082 and 2.080. They are not exact. It turns out that there's a little bit of difference between those two. In this case, it looks like about 2 millivolts, but again, I'd have a tough time. Now notice what's happened. This one a little bit different. So actually, another thing I probably should tell you about Circuit Maker is you really want to go down to the very last ones when you take a look at the cursors. There are some effects. So here we go. And we'll put the last sine wave D there. I'll move my head out of the way. It doesn't get changed for you people, but and here's C. Okay, so I've been more accurate now that I've gone back to the very last sine wave in this group of 5 sine waves here. At the beginning, we do have some transient effects that occur. So what we see at the very back of this is a little bit better. So now if I take a look, sure enough, I got 2.089 and 2.073, which is a difference of about 16 millivolts, which I think is what we had over here. Let's take a look. If I take a closer look here, that's about as close as I'm going to get. So I'd have to use, let's go up here with D, and that should be 0. Well, it's in micros, so it's very close to 0. Well, it is 0 here. If I go, it's exactly on 0. And then I go up to where the signal is. I see I get something like about 8.4 millivolts. So again, it's a little bit difficult to make these measurements, but you notice that there's an offset. And that offset comes from the input of the op-amp, the imbalance between the two inputs, and it's magnified by the gain of the circuit. So that's the first circuit. Let's get rid of that one. I'm going to load up the last one here. So let's open, and here's the voltage follower circuit. I open this guy up. Don't want to save the other one. In this one, the output is tied back to the input. In this one, the input goes to the plus input. And let's take a look what we discover. Well, before I do that, there's a rule about op-amps. The internal circuitry, when there's feedback, causes the voltage difference between the plus and minus input to go and approach 0. They get as close as possible as they can with the imperfections of the circuit. So whatever I'm putting here is going to end up on a minus input, which is directly connected to the output. So whatever I put in is what I get out. So if I run the circuit, what happens here is in this one, you're only seeing, there's only the A input. Let me click on here. Again, you want to watch 2 signals on the scope. You hit the shift key and click on it. Now I got A and B. Let's get rid of this meter. We don't need the meter. And you go over here. It doesn't look like anything's changed, but actually what happens if I take any, make A bold, you see it's right there. If I put B bold, it's right there. They are right on top of one another. I could put an offset in here and get them so they're not on top of one another, but they are right on top of one another. So the output voltage is identical to the input, or you have a gain of 1. Okay, that's enough for, this is again, experiment 3, op-amp applications number 2.